Okay, we're going to find the centroid and moment of inertia for this beam cross-section. It looks like an eye. It's sometimes called an Ibeam, wide flange beam. Common fundamental shape. A real one doesn't look exactly like this, but it has these elements in it. Now, if you look at this, you can see that it is symmetric. So in other words, it's symmetric about an axis through the center, which means what? Which means that I know where the centroid of the overall centroid is. It's right at the center. I don't have to do any calculations to find the centroid of this. So, you know, on your exams or, you know, in real life, you don't have to do, you can use some common sense here. So I know that y bar is 0.15 meters. In other words, that distance is 0.15 meters. So you don't have to do any calculations for that. Now, to get the moment of inertia, notice that I have to get the centroid of each of the, I've called them 1, 2, and 3 areas. And what do we find? Well, we find that the centroid of that rectangle is there, the centroid of that rectangle is there. Now the centroid for the middle rectangle, guess what? It is dead center, and it coincides with the overall centroid. So the centroid for area 2 is the same as the overall centroid, which means what? Which means that the D2 is 0. D2 is 0. In other words, D1, I've shown D1, that's the distance from the centroid to centroid. D3 also is centroid to centroid distance. It's right there. And we can easily see them. They're 0.125 meters for those. But what do I find? I find D2 is 0 because the centroids are the same. The overall centroid and the centroid of the small area is the same. So to get the moment of inertia for this, then we just fill out the B1H1A1, the B2H2A2, the B3H3A3. You can all do that. It's very straightforward. And then what do I have? I've got my y bar 1 measuring from the base to the centroid. My y bar 2 measuring from the base to the centroid. And my y bar 3 measuring from the base to the centroid. Now it ends up I don't need those for the time being, but because we already figured out our D's very easily. Anyway, once I've done that, I have all of my information here, and I can plug it into my expression that you should basically know. 1/12 bh cubed plus d squared a for each area. 1/12 bh cubed plus d squared a for each area. Plug that in, I get 2.71 times 10 to the minus 4th meters to the 4th. Okay, there is a shortcut. I'm going to show you a shortcut for this. And it looks like this. And here's the idea. So same problem, but with a shortcut. What we're going to notice, first of all, if I didn't mention this, for this wide flange type beam, what is the flange? This is the flange. This is the flange. It's wide. So that's one of the reasons it's called a wide flange beam. So that's that's the flange. Those are flanges. And in the middle we have the web. And so I-beam, wide flange beam, sort of identical. Now, how can I create this shortcut? If I take the web and I break it into two different parts, and then move it out like that, I get this. By moving things sideways, it does not affect the moment of inertia, because you can look at the equations, it doesn't matter. As long as I move things sideways, it's not going to change the moment of inertia. So I can do this, and then I have, half of the web there and the other half of the web there. And what I now have is, if you look at this, this is now a box, a hollow box here. If I have a hollow box, then this is, let's look at it from this perspective. What do I have? I've got an outer box. So I have this outer box here, and I have an inner box here. And I can get the moment of inertia by simply taking the moment of inertia of the outer box minus the moment of inertia of the inner box. And that's it. So if I do that, then what I create is a B outer and an H outer. Well, what do I mean by that? In other words, let's look at this one, since that has all the dimensions. My H outer is that. My B outer is that. So I have 0.15, 0.3 for my outer. That's my outer box. And my inner box, I have a B inner of that and a H inner of that. So, and I've listed them there. So I have BO, HO, BI, HI. And I can then create, my moment of inertia is then 1/12 B outer H outer cubed minus 1/12 B inner H inner cubed. Much simpler calculation. And I simply plug that in and I get the same result. So there is a shortcut, and it's that. Now, when I look at my beam, all these things are pretty simple except one. So in other words, the H outer and the B outer are easy. I just take, those two dimensions that are, given. And the H inner is easy too, because the H inner is simply that distance right there. So H inner is easy. The only hard one is the B inner, and how do I get that? Well, you could go through this exercise of moving it out, and that works fine, but you'll also find that the B inner is simply the width of the flange minus the width of the web. So, or it could be, this is, B outer minus B of the flange. So, or B of the web, rather. Sorry, B of the flange minus B of the web. So, this is the only hard one to get. Once you have that, then this becomes a very simple calculation, and it saves a lot of time. Now, notice that if my beam cross-section looks like that, I cannot use the shortcut there. I can only use the shortcut when there is symmetry about the x-axis here. So do not use the shortcut on a shape like that. And so, we can only use the shortcut when the beam is symmetric about the x-axis through the centroid. Okay, so only for pure symmetry. Okay, so what I want you to do is to find, for this situation, find y bar and the moment of inertia about the centroid. And I want you to use the shortcut for this. So pause the video and do this problem. Okay, I assume that you've done that, and then, so what do I have? I just need to get my dimensions, and so this is the given information here. And so my B outer is that. My H outer is the sum of those. My H inner is that. The only thing I need to calculate really is my B inner, which is the 0.05 minus the 0.15. So 0.05 minus 0.15. I get 0.35. So I now have all of these, and I simply put it into the expression 112 B outer H outer cubed minus 112 B inner H inner cubed, and I get that. So much simpler calculation than it is to break it up into 3 areas. And the other thing is that I should mention is that basically, for many practical purposes, not completely, but an I-beam is the same as a box. It's the same thing in a sense. There's some differences when we get down to it, but for what we're doing, an I-beam and a box are the same thing. So that is a little bit, it's illustrated with this particular calculation. Okay. Now, let me say one other thing, and that is that when we use an I-beam, well, we use the I-beam like this. This is when we use an I-beam as a beam in practicality. We don't, so it looks like an eye. That's what we like. It has better performance. Why? Because it gives us a bigger moment of inertia. We want a big moment of inertia. We don't put our I-beam down like this. That's an H. We don't turn it on its side. If we calculate the moment of inertia of this, we're going to find it's lower than the moment of inertia of this. So don't do that. Don't do that. In most cases, well, put some numbers on it depending on, but in almost all cases, the H has a lower moment of inertia than the I. And why is that? Because if you start looking at the numbers, you're going to find that the d squared A term gives us the big moment of inertia. So the d squared A helps us a lot. And why? Because as we push material away from the centroid, that helps us. It helps us. It gives us a stiffer beam we're going to find. So because it gives us this d, and since it's d squared, it helps a lot. So use an I, not an H, because of the bigger moment of inertia. All right, so now we want to put together what we've learned, and so I want to find sigma at the point of interest. Now, in this particular case, I'm going to give you the point of interest on our beam, and sometimes you're going to have to find the point of interest yourself. Other times I will give it to you, saying I want the stress at that particular point. For this particular problem, I am giving you the point of interest on the beam, and I'll show you where it's at. Okay, so here's our beam here, and I've given you the reactions and the loads, and this is the beam cross-section. Beam cross-section is just a simple rectangle. We'll start out with a simple rectangle with a B and an H, and my point of interest, so I'm showing where the point of interest is. So I have to show the point of interest along the beam and then on the beam cross-section. So it's located right in here, 4 feet from the left end is the point of interest, and it's located just off the bottom here, 0.1 feet off the bottom. So that is the location of my point of interest. To be able to solve this problem, I'm going to draw the shear and bending moment diagrams. This is the way to do these. There are other things you can do, but I want you to draw the shear and bending moment diagrams and find the normal stress sigma at the point of interest. Okay, so we can all do this. I go up 10, over, down 8, over, down 12, over, up back to 0. I get my areas. Now in this particular case, because I want the moment at my point of interest here, oops, didn't quite then I'm going to break it up into area 1, area 2, area 3, and area 4. They're all rectangles. You can all get them. There are the areas. That means that I get my moment diagram. I go up area 1, go up area 2, go up area 3, go down area 4. And, okay, I'm now going to use my expression. Sigma is equal to minus my over I. Well, what's my moment of inertia? So the I is easy. It's 1/12 BH cubed. It's just a rectangle. I don't have to find this. I know where the centroid is. I don't have to find the centroid. So if I give you a rectangle, don't make it too complicated. It's just 1/12 BH cubed. Don't even think about it. It's only when I give you more than one rectangle that there's some work involved. If I give you one rectangle, it's just 1/12 BH cubed. That's it. So I get my I there, and that I then goes in that location. So I have one of the three things. One of the other things I want is the moment, M. Well, how do I get the moment M? Well, the moment M comes from where? There's my point of interest, and I get it from my moment diagram, 24.88. So, very simply, based on what we've already done, or what you've already done in life, I get the I from, we've reviewed it, from methods of getting the moment of inertia. The moment from our moment diagrams, which you've done many of them. And now the only, strangely enough, the actual easiest thing to get is what students struggle most with, is this Y. And we have to remember the definition of Y. What is Y? Y is the distance from the overall centroid of our cross-section to the point of interest. So it's quite simple. It's 0.15, but it's below the centroid, so it's negative. So I'm going to put in my negative sign for Y. And so when I'm going to give this to you in this sort of manner, just fill in the blanks. And so what do I have? So remember the definitions of these terms. So that's my equation. Sigma is the normal stress at the point of interest. What do I mean by normal stress? Here's my beam. And remember how we drew our stresses looking like this. And it's a normal stress. Why? Because, there's my surface. These arrows are normal to that surface. So it's normal stress. That's why we call it normal stress. We have to remember that because we're going to do shear stress, which is parallel. Normal stress is perpendicular. Shear stress is parallel. So anyway, sigma, normal stress at the point of interest. M is the moment from the moment diagram at the point of interest. So remember, it's got to be at the point of interest. I is the about the centroid of the entire cross section. So remember that. We're always, so if I don't specify the axis, which I won't, I'll just say moment of inertia. You have to know that it is the moment of inertia about an x-axis passing a horizontal axis going through the centroid. So I'm not gonna give all the details of this. I'm just going to say moment of inertia. You need to know that we know there are infinite numbers of moments of inertia, You need to know that when I just say moment of inertia, I mean moment of inertia about a horizontal axis through the centroid. And then y, this is the one that people get stuck on, is the distance from the overall centroid to the point of interest. Up is positive, down is negative. So distance from the overall, so we find the overall centroid, then we find the point of interest. That is what people stumble on. So this came from the moment diagram. This is my y, which is below the centroid, and this is the I that we calculated. We just plug that in. Do your units. We get 1791 kips per square foot, KSF. And we get a positive sign. Notice, because this comes with the equation, right? That's that one. And then I've got this. What is the positive sign? The positive sign means tension. The fact that that's positive means tension. That is... Now, does that make sense? Yes, it does, because look where my... First, notice my moment diagram. My moment diagram is all positive. If it's all positive, we know that the deformation is looking like that. If the deformation is looking like that, then I have what? At the bottom portion, I have tension. At the top, I have compression. And look, I'm below the neutral axis, so that's tension. So you should double check it to make sure that your signs, if you carry your signs through properly, you will get the right sign here. But it helps to double check it with just common sense and what we know, which is that tension is positive. Okay, we have the same beam and everything like that. What I want you to do is find sigma max, which is the maximum stress in tension. I'm looking at tension in the entire beam. So I'm a maximum stress in tension for this problem. So it's the maximum stress in the entire beam. Well, what does that mean? You have to find the point of interest. I'm not giving you where the point of interest is. You have to find it both along the beam, along the length of the beam, and on the cross section. So I want the maximum tension here. Well, how do I get it? Along the length, the point of interest is going to be at M max. So I look at my moment diagram down here, and what do I find? Oh, there's M max, so my point of interest along the length of the beam is going to be in here. On the cross section, I have to get what? I got to go far away from the neutral axis to get the maximum tension. Why? Because remember, our basic sketch of stresses looks like that. Well, I have to get, down here at the bottom is going to be tension for this one. So I'm going to be at the bottom. Up here at the top is maximum compression, but I didn't ask for maximum compression. So there is my point of interest on my cross-section at the bottom. There it is along the length of the beam. So given that, I take the moment from the maximum is there. Now what? Now my I stays the same. The I doesn't change. That's the 1/12 BH cubed. It's the same everywhere on this beam. Since my point of interest is there, what? My y distance is here, but it's below the centroid, so it's negative. So it's going to be the sum of those two, which is 0.25, but it's negative, so negative 0.25. And then again, so I plug this all in, I get that. I follow my signs. I have a negative there, so I have positive there. And so my result is that. Okay, I want you to work this one. So I'm giving you the point of interest here at that location and there at that location. I want you to draw the shear and bending moment diagrams, and I want you to find the stress at the point of interest. So pause the video and work this problem. And notice it's an I-beam. Use the shortcut to get the moment of inertia. Okay, assuming that you've paused it and done it, let's go through it first. Well, it's easy to get the reactions. The reaction is 10-10. How do I know that? Because this is all symmetric. Everything is, the loads are all symmetric, so I can just look at it and go, oh, total of 20, well, then I have 10 here and 10 here. Everything's symmetric. So I go up 10, over, down 10, over, down 10, over, up. So get my moment diagram. My area is 40. I go up 40. There's nothing here, no area, so I go straight across, and then this is negative 40, so I go down. Now notice we have a special name for this, and there's no shear in this region, but we have bending moment. So this region is what we call pure bending. It's pure bending, there's no shear in there. So that's, you should know that term, pure bending. So there's a moment, but no shear. So this is pure bending. Okay, the moment of inertia for that. Well, I know where the centroid is, the center. That's easy. Then what do? I convert this I-beam to a box. Looks like that. There's my outer dimensions, those two. My inner dimensions, you can get those right there. And so I have my B outer, H outer, I have my B inner, H inner, and I do 112 B outer, H outer cubed minus 112 B inner, H inner cubed, and I get my moment of inertia. So that's one of my, I'm using this expression, sigma is equal to minus my over I. I get one at a time. Got the I. Well, my point of interest is there, so what's my M? Well, the M is going to be 40, so got that. So got those two. I have to get this one. Like I say, that's the only one people tend to miss. It's the easiest one, but it's the distance from the overall centroid to the point of interest. And so there's my centroid, there's my point of interest, so that distance right there is 0.3, and it's below, so it's negative 0.3. I plug everything in, oops, and that's my answer. It's positive, meaning it's tension, which makes sense. All right, I'll stop there.